Welcome, mariners. Today, we're diving deep into a critical skill for modern navigation, integrating satellite meteorology and oceanography to make safer, smarter decisions. We'll look at how to synthesize data, both at sea and in port, transforming a flood of information into actionable intelligence. This isn't just about having the latest tech. It's about using it to see beyond the horizon. Let's set the scene. You're on the bridge of the MV Ocean Sentinel, a post-Panamax container ship, 4 days out from Bison on a voyage to Los Angeles, making a steady 18 knots. Your bridge is state-of-the-art, equipped with ECDIS with weather overlay, a satellite weather routing system, and an integrated bridge system. Suddenly, the data starts painting a worrying picture. Your second officer reports, "Captain, the latest satellite imagery shows dense, rapid cloud growth about 400 miles ahead of our position. The weather routing system is already suggesting a course diversion to the south." The chief mate, looking at his screen, adds, "Our ECDIS overlay confirms it. The predicted wave heights are peaking at 8.5 meters, right along our current track." As the master, you know that one piece of information is just a single brushstroke. You need the full picture. You ask for a cross-check. The second officer consults the Navtex. "We have a Navtex warning, sir. A developing tropical low is moving northwest, with winds expected to reach Beaufort force 9. The pieces are falling into place. The barometer has been dropping steadily." Now you have convergence, the satellite images, the numerical model from the routing software, the official Navtex warning, and the physical reading from your own ship's instruments all tell the same story. There's a storm brewing, and you're headed straight for it. The chief mate makes a recommendation. "Based on this, I recommend we reduce speed immediately and alter course 25 degrees to the south to give the system a wide berth." As master, you agree. The decision is logged, and the engine room is notified to reduce speed. This is integration in practice. It's not just about looking at one screen. The integrated bridge system is a powerful tool here. It fuses the satellite cloud images with numerical weather models. It combines this with data from the ship's own motion sensors and even analyzes sea clutter from the radar. The output isn't just raw data. It's a clear operational picture. You get real-time risk zones plotted directly on your chart, a prediction of how the ship will behave in the developing seas, and even an estimate of the fuel consumption impact for your new course. So, what were the specific actions taken? The vessel alters course south, away from the storm's path. Speed is reduced from 18 to 14 knots to lessen the impact of the waves. Ballast is adjusted to improve the ship's stability and metacentric height. On deck, crews double-check all container lashings. On the bridge, manning is increased to ensure constant vigilance, and the engine room is placed on standby, ready for any maneuver. The result, the Ocean Sentinel successfully skirts the core of the storm. The ship experiences some heavy weather, but rolling is reduced by an estimated 40% compared to what it would have been on the original track. Most importantly, there is no container damage and no injuries to the crew. The extra fuel burned is a small, acceptable price for the immense safety benefits. This proactive, data-driven decision prevented a potential disaster. Now let's shift our scenario. The same vessel, MV Ocean Sentinel, is now berthed at a container terminal in the port of Los Angeles. It's a calm morning, but the forecast is for a strong afternoon sea breeze. More subtly, offshore buoys are detecting a long-period swell, generated by a distant low-pressure system that is due to arrive at the port. During cargo operations, the port's weather station is feeding real-time wind and swell data directly into the terminal's operating system and the ship's own ECDIS. Suddenly, an alert flashes. The swell is increasing rapidly to 2.5 meters. Wind gusts are hitting 30 knots. The cranes are approaching their operational limits. The terminal planner radios the bridge, be advised. Our terminal weather system predicts wind gusts will exceed crane operational limits within the next 30 minutes. We recommend pausing heavy lifts. On the bridge, the chief mate checks the ECDIS overlay. Confirmed. The swell direction is aligning with the berth, which will increase surging. The master takes decisive action. Stop all heavy lifts immediately. Instruct the terminal to secure the cranes. We can switch to discharging lighter containers if the conditions permit. He then turns to the bosun on deck. How are the mooring lines? The bosun reports, lines are starting to surge, Captain. The master's orders are clear. Rig additional breast lines and spring lines to counter the motion. Let's get ahead of this. Here, integration happens between the ship and the shore. Shoreside weather radar, data from offshore buoys, information from the port VTS, and the ship's own anemometer are all cross-validated. This creates a unified, real-time understanding of the risk. The actions taken are swift and precise. Heavy lift operations are suspended. Extra mooring lines are rigged to secure the vessel against the increasing surge. Ballast is adjusted to reduce the ship's motion at the berth, and a toolbox talk is held with the deck crew to ensure everyone understands the situation and the plan. The result, by acting on integrated data, a potential incident involving a crane or parted mooring lines is averted. Operations are paused temporarily and resume safely once the conditions improve. No damage, no delays, no danger. So, why does this integration matter so much? Without it, you face data overload. One screen tells you to go north, another says south. Conflicting information leads to hesitation and slow, uncertain decisions. But with integration, you achieve early detection of hazards. You get more accurate predictions because multiple sources are confirming the same trend. This allows for a swift, confident, and coordinated response. Technology enhances, but does not replace, good seamanship. The core principle is that cross-checking data prevents error, and early action prevents casualties. This coordinated response relies on every team member knowing their role. The master has the ultimate responsibility for the final decision. The chief mate is focused on stability and cargo safety. The second officer is the primary guardian of weather monitoring. The chief engineer ensures the machinery is ready to respond to any command. On deck, the bosun manages the mooring and deck security. And in port, the terminal planner is the crucial link, providing shoreside weather intelligence. To perform these roles effectively requires a deep level of knowledge, understanding, and proficiency. You need knowledge of satellite meteorology, weather routing software, ocean current models, and the capabilities of your integrated bridge system. You must understand that combining multiple sources increases accuracy, and that a correlation between different data types validates their reliability. True proficiency is demonstrated when you can seamlessly overlay weather data on your ECDIS, correctly interpret model outputs, apply those insights to make operational decisions, and communicate clearly across the entire ship and shore team. This approach isn't just good practice, it's embedded in our regulatory framework. From SDCW's requirements for competence in using electronic navigation aids, to SOLAS's mandate for voyage planning, to the ISM code's focus on risk assessment, the message is consistent. We must use all available information to ensure safety. MARPL benefits by helping us avoid heavy weather where a pollution incident is more likely. The MLC and ILO are upheld by reducing crew fatigue and stress, creating a safer workplace. Using integrated weather data is a direct action that satisfies our obligations under these many conventions. So, what are the key takeaways? First, always use integrated overlays on your navigation systems. Second, during cargo operations, adhere strictly to real-time weather limits. Third, be proactive in adjusting moorings and ballast based on forecasts, not just current conditions. Fourth, ensure the machinery is always in a state of readiness. Fifth, meticulously log all weather-related decisions and the data that supported them. And finally, conduct regular training and drills using your vessel's specific systems. By embracing the power of integrated data, we elevate our profession. We move from being reactive to proactive, from being navigators to true maritime risk managers. Thank you for watching, stay safe, and remember to subscribe for more insights into modern seamanship.